Hi everyone, I'm Prashant Kannan. I'm part of the host networking team at Meta, and on behalf of all my collaborators listed here, I'm going to present NetEdit, an eBPF orchestration platform that tunes the host networking stack for Meta data center fleet. For background, Meta operates over 20 data centers with varying hardware configuration. Zooming into one data center, the picture on the top, we see thousands of services running in a shared server pool. This is a very diverse network. We have diversity in both hardware configuration and service traffic characteristics. So, how do you orchestrate this network for optimum performance? This is the problem we're trying to solve here. NetEdit is a bundle of abstractions that service owners and networking experts can collaborate with to optimize our network. Let us first look at a few examples. Problem 1. This is from our physical network. Can you reliably tag every packet, even the very first packet in a connection, based on the RTT? Why is this important? This allows the switch queues to apply differential treatment based on the RTT. Refer to our NSDA talk um, in 2024 about DCTCP deployment for more details about this problem. Problem 2. One particular service A, determines that bursty ingress traffic impacts performance. We identify a potential solution to tame these bursts, for example, by reducing the receiver window advertisement. I'll talk more about such features in a later slide, but for now we have a problem and a potential solution. How do you effectively run a small scale production experiment for this service and quickly vet this idea? Lastly, we could have multiple such tuning features that need to coexist for the same service. Can we deterministically apply all these tunings? Now, taking a step back, you need a platform that supports experimentation, that provides the ability to manage both default configuration and custom tunables based on service needs. This whole system has to be extremely reliable, natively support A/B experiments, and should also be highly available. In the last slide, we looked at a few different problems that need to be solved. But what options do we have? First, we could make the services that run in user space directly call SIGCOMM'24. This means a library that needs to be deployed per service, and this adds a service dependency. We could also work with routes. Routes provide most of the settings that we need, but we risk messing with the routing table. This is another dependency that we wanted to avoid if possible. Syscuttles or kernel modules don't provide the fine-grained control that we require. BPF was a preferred choice since it had the right flexibility and the level of control we needed. This allowed us to operate from specific packets all the way to uh, all the way to implementing fleet-wide defaults. Our solution in the end was to build multiple tuning features that can be orchestrated together in a platform. Okay, let us look at some example tuning features and how beneficial they are to both services and to the network. I'll do this in two parts. Here, I'll talk about some simple transport techniques that I'll call tuning features and some sample wins that we got while we deployed this. Later in the talk, we'll see how these features coexist in an experiment where we turn down the entire platform, go to kernel defaults, and measure performance. First, the first tuning is the initial congestion window per connection. By changing this, we can reduce service visible latency for typically for short-lived connections. Uh, this has shown to yield up to 30% faster image generation for an AI service. Second, adjusting the per packet receiver window can help tame bursts. For storage services, we see that this yields up to 100% faster storage reads. Increasing MSS and thus adopting jumbo MTU leads to efficiency wins for both the network and for the host. For an ad service, we saw 6% CPU utilization savings through this tuning. Lastly, changing intra-region congestion control reduces retransmits that we see and overall improve the P99 latency for user visible services up to 40%. This is just a snapshot. Please refer to the paper for more details about both tuning features and the appropriate wins. The tuning features we saw just now need to coexist, sometimes on the same server. They also need to move as services migrate between hosts. Different tuning features have different levels of maturity. Given all this, let us first define some requirements to manage these features. 1. Be developer friendly. Allow feature developers to iterate fast, try out ideas in production, and hide eBPF attach point complexities. 2. Provide high availability guarantees, just like the Linux kernel. For example, restarting NetEdit or a bug that causes crashes should not implement the eBPF, should not impact the eBPF data plane. 3. Um, Provide context specific orchestration. This is an efficiency goal. We can reduce the overall operation cost by lazy attaching features in reaction to either infra changes or service migration. 4. Minimize dependency. Try to be transparent in the sense, do not tie the fate of host network tuning to either services or the network. Safe deployments. Do not bring down the network if NetEdit service is down. Um, to do this, having the ability to test all the components, roll out regularly, and have observability while we deploy, and possibly a fail open design would all help. Okay. Now, who are the users of this platform? Understanding the users and mapping requirements we just discussed to users um, would really help. One, a service is a service owner. The first is a service owner. Service owners care about network performance and reliability. Their interface to NetEdit is the policy store. Through this, they can specify service boundaries and configure one or more tuning features that they care about. We also have default or broader policies that apply to every service in a given region. Second is network experts. They typically work on prototyping, uh, A/B testing, and deploying tuning features. A tuning feature, like we've discussed so far, is a collection of one or more eBPF programs. Deployment flexibility, ability to test, and observability during deployment are the most important factors for this group. Lastly, infra engineers manage the whole platform. They care about designing abstractions that take on minimum dependency on the rest of infrastructure. In the paper, we discuss about one special tuning feature called Touchstone. This is mainly used by infra engineers to test NetEdit primitives. For example, think of a major NetEdit infra change. How do you test this? Um, Through the touchstone feature, we can canary this change to part of the fleet without actually impacting any of the tuning features by impacting only the touchstone feature. This helps reduce production impact and get higher signal for new infra primitives. In the next three slides, I'll cover the design and salient features of NetEdit. In the picture here, we have a bird's eye view of NetEdit and its interfaces. All of the NetEdit abstractions are shown in the middle box. NetEdit consumes policy and knows about services through its interfaces shown in the top. In the bottom, we see NetEdit's interface to kernel and eBPF through the BPF adapter system. The different abstractions listed in the middle have different availability requirements. For example, metrics exporter should be highly available to support data plane counters even when the rest of NetEdit is down. So we typically run this as a separate process. I'll talk about key data plane and control plane components in the next slide. Okay, let's look at four ideas for data plane. I'll use one eBPF program, the scope resolver, as an example throughout the slide. NetEdit uses destination IP address to classify connections. For example, is a connection within the same rack or is it going across geographic regions? We've made a separate tuning feature called Scope Resolver to give us this answer. Since many transport features require scope to decide policy, this particular eBPF program has to always run first. So the key idea here is to impose a deterministic ordering across uh, all the eBPF programs for every attach point. And we typically do this for attach points where more than one program can get executed. Once we run the scope resolver and we have a result, this result has to be made available to all the other eBPF programs. We do this through shared maps. A shared map is nothing but an eBPF map that is pinned and shared with programs across all the attach points. Lastly, NetEdit itself is a user space process, so its lifetime is not guaranteed. We could be updating NetEdit, or we could have a buggy version that keeps crashing. For features that expect to run all the time, this could cause disruption. We solve this by separating eBPF and edited lifetime by pinning eBPF programs. We pin the eBPF programs through a special file system, and as a result, this brings a new problem. This problem is about eBPF versioning. Our goal is to maintain one active version per feature across the entire fleet. You may wonder, what about existing connections? Won't they still be using the older version? That is true. What we've seen is sometimes connections can last in the order of days or probably even longer. Therefore, to um, force our intent and have one single version, we use the concept of eBPF iterators to retroactively enforce policies. Okay, I touched upon multiple ideas in the data plane. For control plane, let me just focus on how policies are handled. Policies are authored outside NetEdit. We maintain a single repository so that user intent is very clear. Policies are written in a flexible configuration language. This language allows us to express requirements regarding both locality and granularity. At a high level, you can think of a policy as a match action rule. For instance, match match on any intra-region connection and take the action of specifying a congestion control algorithm. These policies are refreshed periodically. This could be in the order of seconds or minutes, depending on the staleness guarantees per feature. The policy engine running within NetEdit constantly polls both the policies and other infra components to get an up-to-date view of the infra. An example of an infra refresh is getting a list of all active services on a given host. Thus, when policies are read, this current infra state will help us decide which policies have to be updated. As part of policy update, we follow a lazy attach mechanism. For instance, the very first active policy triggers this whole lazy attach mechanism. You can roughly think of this as memory demand paging. The fixed ordering capability I discussed in the previous slide for data plane ensures that irrespective of how policies change, the eBPF execution order is always preserved. Okay, we discussed about features and the overall NetEdit design. Next, let's talk about deployment. The NetEdit state is constantly changing. One, we push code changes to the fleet very regularly. Two, services could be running A/B experiments in prod for different tuning features. Three, from the config side, policies can be changing, and this has its own independent blast radius. For all these three, there is you can think of it as a universe of concurrent tests uh, that we have to support without compromising reliability. To do this, we track both short-term and long-term trends. In short-term trends, we focus on feature errors and data plane statistics that are aggregated and alerted upon. Since a netted data plane is always attached, we have to consider observability. This is an interesting operational detail, but what we had to do is separate counter aggregation into a separate process to solve this case. Um, The long-term validator verifies if the policy intent matches the current state of the world. By leveraging external sources of truth, we can independently audit and catch any end-to-end issue. Please refer to the paper for more details about observability and deployment experiences. Earlier in the talk, I covered some incremental wins through NetEdit features. Here, let's see what is the impact to our network if all of NetEdit goes down. To test this hypothesis, we ran an experiment where we turned off NetEdit for an entire across an entire region for more than an hour. Through this, we saw high incast patterns and aggregate drop in throughput from the network in the order of around 10%. Looking at the host, this translated into high retransmit events, specifically retransmit timeouts. Both this had a correlation for services. Here, we observed a correlated impact on service metrics like QPS and latency. Please refer to the paper for more details on performance numbers. In summary, we showed how NetEdit and its abstractions support eBPF based tuning as a service. Data plane capabilities are at the heart of what NetEdit can support. To this end, we've upstreamed all the kernel capabilities that NetEdit uses. For example, the structops interface to implement congestion control, and even the iterator interface to enforce ad hoc policies. I skipped a lot of interesting details in the interest of time. For instance, how unit tests and production BPF features coexist. Uh, we also talk about interesting kernel or infra bugs that we've seen. In terms of lessons learned, one specific area is eBPF attach point selection. For instance, the same tuning feature is available through more than one eBPF attach point. We discussed two interesting cases. One, in the first case, we saw a 200x improvement in performance by switching from one attach point to the other. But in another case, we broke a tuning feature since we did not fully understand that eBPF kernel nuance. Please refer to the paper for more interesting details on this. Every new eBPF interface that we take um, introduces introduces some uncommon kernel paths. Despite all of our testing methodologies, which are discussed in the paper, we still occasionally discover bugs in production. Failures here are high risk since there is a potential to bring down the entire system. We look forward to working with the research community on rigorous testing frameworks. One potential area is to test the interaction across eBPF programs or test the eBPF kernel interface as a whole. Thank you for your time. Now I'll open it up for questions.